Any questions? It's all right. Okay. So this is the momentum equation. Okay. So if you have to break this down, okay, right, you could break this down into three if you wanted to. Okay, you could say in terms of vector. All right, you could say, okay, here. All right, it will break into three. All right, and instead of writing in terms of vector, what's this rubbish here? All right, you can say this is x, this is y, this is z. Remove all the vector. Okay, remove all the vector. So this becomes x, the y component, and the z component, x, y, and z. Okay. All right. So previously was a vector equation. These are in the components. Is that okay so far? So most of the time, you won't have to solve this, but in case you do, just here. All right. Most of the time, no need one. All right. Most of the time, usually steady state. Okay. So this term, all right, the d on dt of anything is equal to 0, so you can get rid of the first term. All right. And normally, all right, but not all the time. No exam, they just like to throw you off a little bit, make you integrate. Normally, let's say if the velocity was okay, if the velocity was constant across the area, okay, example, all right, constant velocity. Okay, example, let's say we had the pipe, something like this. All right, it come in here and go out here. Right, some sort of nozzle. We draw a control volume. All right. Obviously, we draw it where we know the information. I don't draw it where we don't know the information. So we draw it in the inlet, cutting the inlet outlet. Okay. So this feature. So this one only in the x, so you only need to worry about this one. Okay, in this case, this one no need. Alright, because steady state. Okay, this one, sum of forces in the x. I haven't talked about forces yet. So this one, rho v dot n dx is equal to rho V out, all right, times V out times area, okay, A out, minus rho V in, area in. Okay, because it's constant, so there's no need to integrate. So where the V dot n, the normal vector is this way. Okay. Normal vector is this way. This one, both velocities are positive in this case. Right? This is the x direction. Okay. This is the x direction. Right? Positive x direction. Okay? So V out and is larger than 0, and V in is larger than 0. They are both positive. They are both going in the positive direction. Is that okay? So rho V out. So in other words, it is actually rho V out A out is actually m dot out V out minus m dot in V in. is equal to sum of forces in the x. This is the x component of velocity, x component of velocity. Is that alright? Okay. So rho v out a out is actually m dot out. Rho v in a in is actually m dot in. So that's how I made that one. Normally you use this one. Okay. Normally, yeah. Alright. Alright. Because, right? So in this case, constant velocity, velocity normal to the control volume, and both velocity in this case positive. The negative here is because the only reason why there's negative here is because when you're going in, the in velocity and the normal vector are opposite directions. That's why here it becomes negative. Alright? Which one? This n here? Sorry, not drawn correctly. It's pointing outwards. Okay, this n vector. Alright, n always points normal to the control volume. Or always points normal to the control surface. Is that okay so far? Alright. Okay. Let's do next. Alright, I forgot to talk about forces. Alright. So on the right hand side, we normally have forces. Okay. So forces. Alright. There are a few that you need to worry about. Alright. Normally there is external forces. Alright. Sometimes your control volume is held in place. Alright. Maybe in this case, your control volume is this nozzle. Alright. Maybe you need some hand or something to hold it in place. Alright. If not, it might move around. Okay, like an anchoring force. Is that alright? So you could have an external force, like an anchoring force. Alright. You could have what else you could have? You could have viscous forces. Alright. Normally most of the time is 0. Alright. Because sometimes your control volume, okay, in this case, your control volume is just this blob of fluid here. Okay. If your flow is going through here, if there's other flow here and here, then there could be viscous forces between the layer, between the streams of fluid. Okay, no? Between the fluid inside the controller and the fluid outside, they could be rubbing against each other. Alright? So, but normally in this unit is 0 lah. Okay? This is more advanced stuff than got. Alright? Normally not considered in this unit. Then the other one which we do consider, pressure. Alright, and F, gravity. Alright, pressure, I'll teach you how to work that out. Then we will do that soon. Okay. So let's do an example. Okay. The way I'm going to do, the example goes from easier first, then it gets increasingly more complex. Alright. Normally we do over about 2 hours worth of examples. So we start easy first. Okay. So let me know if not easy enough. We have, let's say, one pipe. One converging pipe like this. Alright. Here, the area is equal to 1 meter square. Here, this area, maybe area equals to 0.5, 0.43 meters square. 0.3. Alright. So, obvious, normally we draw the control volume where we know, so don't draw all over the place. Okay, make sure you draw like this. And I draw in blue. Okay, so control volume, you draw like this. Okay, We draw normally at the surfaces where we know the information. Alright. So let's say this one, there is an anchoring force here, right, to the ground. Hold this pipe in place. Alright, this contraction. Remember there's more of this pipe now, okay, which I didn't where I cut through. Okay, so the anchoring force could come from my support or could come from the other parts of the pipe. Don't worry lah. Okay, there is F external to hold this pipe in place. Is that alright? Okay, so it could come from here. Alright. Okay, it could come from either support or from the other pipes, this pipe or whichever that's supporting this joint. Okay, so let's say 1 meter per second velocity coming in. First step, let's find B out, question mark. Okay, so that one we did like last week. I think M dot in is equal to M dot out. Oh, I forgot, right? This is steady state now. Alright, you can assume steady state in this problem unless the problem tells you so now. Okay, M dot in is equal to rho A in V in is equal to rho A out V out. Okay? What's the blinking dot there? I don't know. According to bars there. Okay. Alright. This is blinking dot. Okay. So, this case, now you can take rho equal to 998. Alright. But here I think this rho to rho will cancel off. A in 1, V in 1 is equal to 0.3. I think V out. I think V out is equal to 3.33 meters per second. Is that okay? 1 divided by 0.3. Yeah. Is that alright? Any questions? Alright. So second part, first part we found out the velocity. Second part, they might ask you calculate the external F external. Okay. So because this is pipe, alright, there's no guarantee that the pressure is the same. So let's say the pressure, again, all in terms of gauge pressure because only the difference matters. Okay. So this part here, the P is atmospheric, is equal to 0. This part here. But not in the pipe. Alright now. On this outside here, remember this control volume must be box, right? Okay. So, and this is the positive X direction. Okay. The pressure here maybe P is equal to 100 kPa. Say. The pressure here, I'm just guessing. Later on we actually can calculate the pressure using Bernoulli's equation, but I just guess now 200 kPa. Okay, say for example. Alright. So in this case, let's say M dot out V out minus M dot in V in is equal to F sum of forces in the X. Okay or not? Alright, which is equal to F external, X component anyway, plus F pressure. Alright, because in this case, F viscous is equal to 0, no viscous forces acting in our control volume, and plus F gravity. Alright, gravity in the X direction is 0. Okay, these are the normal four usual suspects we need to worry about. In this case, these two are 0. Okay. one is 0. Is that okay? Right or not? Okay, m dot out. Alright. M dot out is row A out, D out. Alright. Times V out minus row A in, V in, multiplied by V in is equal to F external in the X plus here F pressure is complicated. Let's do the easy one first. Alright. Okay. Now, so in this case, here, all these forces that we are looking at on the right hand side is all forces of not the control volume acting out, but of the forces of outside acting on the control volume. Alright? So all this right hand side is forces acting on the control volume. Is that okay? Alright? So pressure force on the left hand side is actually the pressure here 200 kPa times A in. Pressure times area is a force. Alright? And it's positive because that force outside acting in will be from left to right. It's in the positive direction. Is that okay? Alright? On the right hand side, alright? Okay? I have 100 kPa. Alright? Area in is what? Area in is area in. Area out, sorry. But this is negative. Alright, look carefully here. I draw negative. Why? Because 100 kPa, yes, inside here is 100 kPa, outside here is 100 kPa. Alright, just before and after the control surface. Alright, but we are not concerned about the pressure inside acting out. We are concerned about pressure outside acting in. So outside here 100 kPa pushing on our control surface, the force vector will be this direction. Right or not? Will be from right to left. Right to left is a negative force. Right or not? Okay? And some of you might miss the last one out, but that's okay lah. Because this time we use gauge pressure. By right, the control volume, no matter how you draw it, this area will always be same as this area. Okay? If you try to follow closely here and so on, yes, you can distort the thing a little bit, but the projected area, which is what the force in the x direction that works on anyway, will be the same. Alright? So no matter how you draw it, the projected area on the left hand side and the projected area on the right hand side will be the same. Correct or not? Right? If I squash it flat, both sides are the same. Okay? Projected area means is equivalent to squashing it flat or looking it straight away in the x direction. So in other words, in this one, if you look at it from the left, you'll see some area. If you look at it from the right, you'll see the same area. Is that okay? So by right, this one, there's also another term here, minus, in this case it's 0 kPa, so it makes no difference, but it will be A out minus A in. Alright, why A out minus A in? A in minus A out, because this is this remaining area here. Is that right? Must be considered. But since the pressure is 0, so if you miss that out, that's okay. But by right, this area needs to be considered, because this area is the same as this area. Is that right? So this area is A out, A in, this area A out, this area here, A in minus A out. Okay? So if you want, you can put in the numbers. 998, A out is 0.3, V out is 3.33, 0.3, velocity out is, no, I messed up. A out is 0.3, velocity out is 3.33, this velocity out 3.33, minus 998, A in is 1, V in is 1, is it? Yeah, V in is 1, multiplied by 1, is equal to F external, the X, plus 200,000. A in is what? 1, minus 100,000. A out is what? 0.3, minus 0. Alright, F external in the X equals, someone punch that into a calculator and see what you get. In the meantime, does anyone have any questions? This part, all right. There's a question in front here. Ask me explain what is A in minus A out. All right. Okay. So remember, in this case, we are looking at the pressure forces in the X direction. So on here, no problem. It's the pressure times area. On here, yes, definitely it's pressure times area here. But the control volume, all right, will also have some area here. Okay, so you need to consider the area outside here. All right, but let's say some other fella say, oh, I'm smart. This is another, you could draw this way, green. Okay, he draw control volume like this. Oh, I'm very smart. I draw like this. Okay, so the green area as far as inlet outlet is still the same, but the green part here is not the same. Okay, not? Alright, between the green and the blue. Alright, but I'm telling you the forces is the same. The forces in the X direction is the same because pressure in the green and the blue is the same. It's atmospheric pressure. And in this part here, although it's sloping, we cannot use the slope area, we need to use the projected area. And by the time you use the projected area on the green, alright, the green's projected area, which I'll draw in blue, in this color blue, will be the same. Is that alright? Because here you actually have a force going this way. By the time you resolve it to this way and this way, it actually comes the same. Alright? The projected area is the same. Alright? In other words, okay, you have a force this way, this way, this way. By the time you resolve it to the X direction, this component times this area will give you the same as this one. Alright? So, whatever you do need to it's alright? In other words, if you got, number one, don't be so smart and draw the box in green. If you draw the blocks in blue, alright, then you can clearly see that there's area here that you need to account for, alright, in the X direction. If you draw the box in green, alright, I'm telling you, you can do out the calculation and you will find that it's exactly the same. You have this area here, alright, this projected area here where the X or the horizontal force or the X force X. Is that okay? Does that answer your question? Alright. Okay. So, what's the answer? Minus 167. Okay. Alright, this number is very big. That's because the pressure I put very high. Alright. Okay. But it wasn't for this pressure alone. Okay. This term here. Alright, listen here. I'm explaining this part here. This part is very important because you can simply do and then you don't realize whether you're correct or wrong. A lot of people do that way. Just, okay, m dot out v out minus m dot in v in. So on the formula sheet also, just apply. Alright? And if you're lucky, then okay. But if you know a little bit of why you're doing it and what you're doing, alright, then it may help you, if you do any mistakes and so on, you realize it. Okay? So this one, alright, this answer is very negative because this 200,000 minus this part here is very big. Okay? But pressure, so the pressure is actually pushing, the pressure is actually pushing out my system that way. My F external force needs to push, to hold this thing in place, needs to push it that way. Okay or not? Alright, but it's really the pressure. Even if I neglect this side, this one will be very negative for the end. Okay or not? Alright, so the pressure is pushing my control volume to the right, so my external force has to hold it back in place. Alright, my control volume will start accelerating away. Alright? But if you look at this part here alone, it's positive, isn't it? This one is bigger than this one. Correct or not? Alright? So, on the left hand side, the fluid alone, the F external force is equal to something positive. Alright? If you neglect the pressure part, the right hand side is positive. Is that alright? What it means is, okay, so for the fluid part alone, for the fluid to go from 1 meter per second to 3.33 meters per second, you need to push the fluid. Right? It needs the external force, which is positive. Positive means to the right, from left to right, to push the fluid. Alright? Because the fluid is going faster, it's actually the fluid's increasing momentum. Alright? If you want to increase momentum, you have to push. Correct or not? Alright? If you are sitting on your billy cart and you want to go faster, somebody has to push you. Alright? From outside. Or you can use your leg to push yourself up. But alright? But assuming you don't do that, somebody has to push you. So this one's the same. You're going from 1 meter per second to 3.33 meters per second. Mass flow rate in and out is the same. Alright? So for you to go faster, the external force needs to push you. Alright? And then external force will be from the chamber or the walls of the control volume and so forth. Is that okay? Alright? Okay. So, alright? So if it is a pipe flow, you need to worry about pressure. Okay or not? Alright, the next problem I do is external flow. You don't need to worry about pressure. Alright? Why you don't need to worry about pressure? Because pressure atmospheric everywhere. So example, alright, I think your experiment, okay, let's do the cup one first. Alright, your experiment, okay, this is the Y positive direction. Alright, okay, so you have your jet, so jet of water shooting up and get deflected 180 degrees. Alright, so the control volume, okay, actually I draw, okay, the control volume, alright, you don't need to draw with law of fluid inside, you draw just here. Okay, so just before the fluid hit the plate, the cup. Alright? Just before the fluid hit the cup, and just after the fluid did the 180 degree and go down. Alright? So there's very little fluid in the control volume, so later we don't have to worry about F gravity. Alright? If you got a lot of fluid in the control volume, then you have to worry about gravity, because G is going downwards here. Okay, G. Okay? But just a very little bit of fluid. Okay? So in this case, we again pressure is atmospheric everywhere. Alright? So the out, the in, and so on is atmospheric pressure. M dot out, V out minus M dot in, V in is equal to F. The external pressure, I already know what it is cup on control volume. Alright? So the cup is pushing on the control volume. Alright? Through this interface here. Alright? Okay? So this one is this one. Why not? Through that surface there, the cup is pushing the fluid or pushing the control volume. Alright? I can expect with this one, that force will be negative. Okay or not? But you can expect already. So if you get positive number, wrong already. Alright? Because that force is pushing the fluid down. Correct or not? Alright? Plus F pressure. Wrong color. Plus F pressure. And that one is 0. Okay, so here, we can already do the Y. We're only interested in the Y direction. Alright? So far, I'm only doing one direction of problems. Alright? Next, I think I'm supposed to do two direction, but I'll do one direction problem. Plus control volume, plus F pressure, plus F viscous. This one is 0. Plus F gravity. Alright? This one is approximately 0. Alright? Very little fluid inside a control volume. But by right, it's actually mg, but never mind. Okay? Because the pressure everywhere is atmospheric, in, out, and so on. Alright? Actually, if you want to be, sounds bright fellow, say, hey, hang on, that pressure at that purple part is not 0. Okay? But actually, yes, the pressure at the purple part is not 0, but it's accounted for here with this purple part here. Alright? So the pressure everywhere except for the purple part is 0. The pressure on the purple surface may not be 0. That's where the cup pushes on the fluid. Alright? So it's actually accounted for in this one here. Okay? Alright? But so the pressure everywhere else is 0. Pressure at the cup interface is accounted for by this term here. So let's see this one. M dot. Let's say M dot is equal to 1 kilogram per second. Velocity is equal to maybe 3 meters per second. Alright? So M dot out, V out, or M dot out is okay. That's 3. So if 3 kilograms, 1 kilogram per second go in, 1 kilogram per second must come out. Okay? It's steady state, huh? Right? Okay, so 1 kilogram going out. The out direction, positive or negative? So here, we normally, if you're not, in this type of problems, if you're not told the velocity, you can assume it go in and come out at the same velocity. Just it do a nice 180 degree turn. Alright? So we assume it's still the same velocity, same magnitude, but obviously the direction is different. This one is going down. So this is negative. Okay, now M dot out, V out, minus M dot in, 1, V in is 3. Okay, now. Is that alright? Okay, this is positive because the in is going upwards. This is the positive. Alright, why positive this way? Okay, equals F cup. So I need to draw a line here. Cup on CV. Y. So your answer is actually minus 3 minus 6. So F cup on control volume in the Y direction is equal to minus 6 newtons. Alright? So the cup is pushing the liquid down 6 newtons. Every force, forces are in pairs, isn't it? They have an equal and opposite. So F liquid on cup is equal to 6 newtons. Okay? So in other words, the liquid is pushing the cup up 6 newtons. The cup is pushing the liquid down 6 newtons. Okay? Any questions? Alright? This equal opposite pair. Right? Huh? Yeah, what's the good? Yeah? Go up. Let's say first, huh? Yeah, go up. Huh? Yeah? No, the pressure here is 0 because out here is atmospheric. All this in terms of gauge pressure, so here is 0, pressure is equal to 0. A in minus A out is this area here. Right? Later I can explain to you more. Right. Any other questions? Okay, so final one, we do the plate. All right. So the liquid comes up and go this way. All right. I draw my control volume here. Okay. All right, everything will be the same. All right. Okay. So all this is still 0. So I need to worry about this one. Okay. All right. So here m dot out is still 1. What's the velocity out in the y direction? Y is this way. Alright? It's actually 0. Alright? Minus m dot in is still 1. Here is actually 3 is equal to F cup on CV in the y direction. So F cup on CV in the y direction is equal to 3 minus 3 newtons. Alright? Why is it 0? Because the velocity is being only turned, instead of turn 180 degrees, it's will be only turned 90 degrees. Alright? So the velocity going out is either in the x direction. Alright? Maybe some part in the x direction, some part in the other direction, and so on. Doesn't matter lah. Alright? Okay? So that in the y component of the velocity going out is 0, right? Because the y is only this way. Okay, that's why it's 0. Here is 3, and then you get minus 3. Is that okay? So in this case, all right, in the earlier case, we had to turn the water 180 degrees. So not only do we have to bring the water to a stop, that's why the force is to bring the fluid momentum to a stop and to push it the other way. That's why you get 6 newtons. Alright? The second one, you only bring the velocity to a stop in the y direction. Then after that, it goes out in x direction. Doesn't matter. It doesn't affect this y momentum equation. Is that okay? Alright. Any questions? Okay. Alright. So, finally, if you wanted to do the y, but we'll do more problems in the other thing. If you wanted to do the x, all right, if this was a purely a two-dimensional problem, all right, you actually the out, half of it goes positive, half of it goes negative. Actually, net is a 0. Is that all right? But we'll explore that further tomorrow. Yeah, tomorrow. Okay. If you were to do the momentum, the x, today I just stick with 1D. Okay. Wait outside. Okay, class coming in. Alright, those need my signature, please wait outside. I think let the next class come in.